At the forefront of consistent progress is the European Panel for Nuclear Assessment, CERN, renowned for its vital responsibilities in atom material science. The broadly famous atom material science research focus has uncovered a staggeringly fascinating finding from its colossal hadron collider that could thoroughly change how we understand the universe. Specialists believe these surprising revelations could uncover the presence of untouchable life in a parallel reality. This important idea has sparked excitement and serious discussion among experts. Could this astounding discovery reshape our understanding of the universe? Moreover, if verified, what critical insights will this exposure offer into the nature of reality itself? Join us as we dive into the recently dispersed revelations, exploring how CERN analysts are breaking their silence on this chilling new discovery that has the potential to change everything we know. The European Organization for Nuclear Research, also called CERN, has been well known for its daring experiments since its founding in the 1950s. It has been at the center of attention several times for good reasons, but its assessments have also raised concerns about the potential risks of black holes, cracks in our universe, and other hazards. One of CERN's most notable and controversial achievements was the development of the Large Hadron Collider, LHC. The LHC is the world's largest particle accelerator. Beginning operation on September 10, 2008, it remains the latest addition to CERN's accelerator complex. Spanning more than 27 kilometers of superconducting magnets and a series of accelerating devices, the CERN Super Collider cost more than $4.5 billion. Many would argue that this money was well spent, as the LHC has resulted in some of the most significant discoveries of recent decades, such as the discovery of the Higgs boson and various other previously unknown particles. This massive machine is capable of accelerating particles around its circular path until they reach nearly the speed of light, completing more than 11,000 laps per second. The LHC achieves this using a series of incredibly powerful electromagnets that produce a magnetic field within the accelerator nearly 100 times stronger than the Earth's magnetic field. Some have expressed concerns about the effects of creating such strong magnetic fields on nearby devices and their potential impact on the Earth's own field. Once these particles reach their maximum speed, they are forced to collide in opposite directions in violent crashes, releasing enormous energy and creating various particles. When these particles collide, a burst of particles escapes in all directions, with most of them lasting only fractions of a second before disappearing. By changing the source of particles, scientists can uncover new ones in this whirlwind. Highly sensitive detectors are placed around the collision sites to record all data from each crash. This amount of information accumulates rapidly and requires immense effort to process. The LHC's experiments produce more than 15 petabytes of raw data annually, which must be meticulously filtered to extract the information scientists need. In 2017, the LHC achieved a significant milestone by permanently storing more than 200 petabytes of data in its tape libraries. To put this into perspective, 1 petabyte is equivalent to around 250,000 movies. But what exactly are they looking for in this data? Scientists identified something unusual with a specific type of quark. Quarks are the fundamental building blocks of matter and exist in various flavors, as defined by physicists. Some of these quark flavors are highly unstable, decaying into different particles almost instantaneously. The beauty quark, with an average lifespan of 1.2 trillionths of a second, became the focus of attention due to a peculiar twist in its decay pattern, which differed from what researchers expected based on the standard model. According to their expectations, when a beauty quark decays, it should be influenced by the weak force and transform into a set of lighter particles known as leptons, either an electron or a muon, with a standard model predicting a 50-50 chance for the two particles. However, the LHC data revealed that these quarks decayed into muons 70% of the time instead of electrons. This discrepancy could exist if a previously unknown type of particle is involved in the process. This has led some researchers to speculate that a new kind of physics might be at work. A new force-carrying particle would imply entirely new physics, extending the standard model and answering many perplexing questions. The possibility of new physics challenges the standard model, which provides our best understanding of how the universe's particles behave. The Standard Model is a scientific framework that precisely explains nearly every aspect of our understanding of the physical world's building blocks. However, despite its accuracy, physicists are aware that this model is incomplete. The Standard Model only describes three fundamental forces: electromagnetic force, strong force, and weak force. Currently, there is no description of gravity or an explanation for dark matter, the universe's most dominant form of matter. During recent experiments, scientists found an anomaly in the data they were analyzing, which differed from the Standard Model's predictions. Although it is not uncommon to find results beyond this framework due to the volume of data produced by the LHC, this particular finding piqued scientists' curiosity and warranted further investigation. What could this new force be? To explain this unexpected discovery, scientists propose the existence of a new fundamental particle, which they refer to as Z', a force-carrying particle. Although this force is the best hypothesis, it is incredibly weak, as no signs of it have been detected thus far. The researchers believe it could interact uniquely with electrons and muons, but the extent of its interactions with Standard Model particles remains unclear. For now, if researchers were to discover new force-carrying particles, it would represent a long-awaited breakthrough in physics. Physicists hope that, if this discovery is confirmed, it will help unravel long-standing mysteries of the universe and deepen our understanding of reality itself. Of old issues, for example, what dark matter is and the role of the Higgs boson in the current day, a few specialists believe that this concealed power could help satisfy one of physics' most critical objectives of the last century: unifying the fundamental forces of existence. According to Elon Musk, CERN constructed the largest and most powerful energy particle collider in human history, the Large Hadron Collider (LHC), between 1998 and 2008. More than 10,000 researchers, numerous institutions, and laboratories from over 100 countries contributed to this process. It sits within a 27 km long tunnel on the border between France and Switzerland, near Geneva, approximately 175 m underground. The very first impact recorded at the Large Hadron Collider had an energy of 3.5 TeV per beam, many times that of the previous world record. The energy later reached 6.5 TeV per beam once the LHC was further improved. Musk noted that the LHC excels at proton beam collision. Additionally, it can accelerate lead beams. Specifically, proton and lead collisions are often conducted for 1 month for researchers testing predictions of various particle physics theories. The primary objective of the Large Hadron Collider is to test the properties of the Higgs boson and search for the wide array of new particles predicted by subatomic particle theories. Hadrons are composite subatomic particles made up of quarks, which are held together by a strong force, similar to how atoms and molecules are held together by the electromagnetic force. Protons and neutrons are two examples of hadrons that are widely recognized. Included are the pions and kaons, which were first discovered in cosmic ray experiments in the late 1940s and early 1950s. The LHC brings two colliding particle beams together so they can interact. The Higgs boson is thought to be a fundamental particle associated with the Higgs field. It is the quantum excitation of this field, much like observing waves in the ocean. The boson resembles a new species in the particle zoo. It lacks the quantum properties of fundamental matter, as well as those of the carriers of quantum interactions such as electromagnetic force, weak force, and nuclear interactions. The Higgs boson was discovered at the Large Hadron Collider, a groundbreaking discovery achieved simultaneously by the two major multifunctional experiments, ATLAS and CMS. It was announced on July 4, 2012, at CERN. At the time, the new scalar boson was found primarily in two rare decay states that provided the clearest signals: decay into a pair of photons, which required a completely quantum virtual process, and direct decay into a pair of Z bosons, the carrier of the neutral weak interaction. Although the discovery of the Higgs boson at the time confirmed the Standard Model, research into this elusive particle did not end there. One of the main discoveries since 2012 was the confirmation of Higgs decay. According to CERN, the study of this elusive particle will continue to evolve during the LHC's third cycle, particularly once the Atom Smasher's high luminosity upgrade is completed in 2029. This will allow the LHC to perform more collisions, giving researchers greater opportunities to detect rare physics events, such as those that do not fit into the standard model. CERN estimates that once the accelerator is upgraded, it will produce 15 million Higgs bosons annually, compared to the LHC's production of 3 million Higgs bosons in 2017. This could help identify different types of Higgs boson hypotheses that go beyond the standard model of particle physics, with up to 5 distinct types of Higgs bosons, some of which may be produced less frequently than the main Higgs. Even before these upgrades, researchers have provided indisputable evidence for a massive Higgs boson. But why does this matter? The Higgs field was immensely significant in the early moments following the universe's creation. It governs the very nature of the vacuum that exists in our spacetime, allowing matter and interactions to exist as we know them, as well as the development of mass in all known fundamental particles. Without the Higgs field, and therefore the Higgs boson, the universe would lack atomic components, stars, and life. This may explain why the Higgs boson is called the God particle. The moniker was popularized by the media following its discovery. It is often attributed to Nobel Prize-winning scientist Leon Lederman, who, out of frustration, referred to the Higgs boson as the goddamn particle because it was so difficult to detect. When Lederman wrote a book about the Higgs boson in the 1990s, he wanted to title it the goddamn particle, but the publishers disagreed and changed it to the God particle. This led to an ongoing debate between the particle's name and its implications for religion, which continues to concern modern physicists. Nonetheless, the significance of the Higgs boson and the Higgs field cannot be overstated. Without it, particles would lack mass under this aspect of nature, meaning there would be no stars, planets, or people. Hence its bold nickname. Apart from the clear need to describe this new particle, researchers continue to study the Higgs boson for 2 reasons. 1. To understand how the physical vacuum we live in originated in the early universe. 2. To determine how this physical vacuum can remain stable. The Higgs field is unique in that it imparts non-zero mean expected potential energy to the physical vacuum, which has profound implications for our universe. Researchers believe that accessing the structure of this energy potential is responsible for the presence of electromagnetic force, with infinite range, and weak force, with a very short range. To achieve this, scientists must explore how Higgs bosons interact with one another, which requires creating pairs of Higgs bosons. The Higgs boson contributes to answering the fundamental question of how all other fundamental particles gain their mass. However, its mass remains unexplained. Any inconsistency in the theory that does not account for this mass causes accidental instability. Quantum fluctuations could disrupt the physical vacuum. Fortunately, this occurs on timescales far greater than the known lifespan of the universe. However, researchers are still searching for additional Higgs boson-like particles that could indicate the presence of new physics needed to stabilize the Higgs boson's mass. All these considerations fuel the pursuit of even more data and, if possible, access to greater collider energy. For this reason, a decade later, many scientists worldwide remain focused on this work. The Higgs boson was first proposed in 1964 and discovered in 2012. Scientists have wondered why it took so long. This is because the Higgs boson is both massive and incredibly unstable. To create such a massive particle, scientists needed to focus a tremendous amount of energy in a small space. They required a high-energy collider. Once formed, Higgs particles decay in various ways, with only a small fraction detectable against the background. Researchers built the largest and most complex detectors to identify such particles. They then analyzed millions of proton collisions to find a Higgs boson signature. In any case, will CERN's operations and discoveries empower us to make tremendous breakthroughs? Or will it lead us to our ultimate end? Researchers have 3 main theories about what CERN is doing. The first and deadliest idea, which has led some to point fingers at CERN, is that the organization is attempting to open a portal to hell. Some believe that CERN's experiments with subatomic particles traveling at the speed of light will propel humanity beyond the gates of final damnation.